We now deal with the Hopf bifurcation. Note that the saddle node, the pitchfork, and the transcritical bifurcations always involve the collision of two or more fixed points. We now consider a new bifurcation that has no counterpart in one-dimensional systems, and it provides a way for a fixed point to lose stability without colliding with any other fixed points of the system. So we now get on to the Hopf bifurcation. Suppose that a two-dimensional system has a stable fixed point. What are all the possible ways it could lose stability as a parameter mu varies? Now clearly the eigenvalues of the Jacobian are key. If the fixed point is stable, the eigenvalues lambda 1 and lambda 2 must both lie in the left half plane where real of lambda is less than 0. Since the lambdas satisfy a quadratic equation with real coefficients, there are two possible options. One, both the eigenvalues are real and negative. So we plot the imaginary of lambda versus the real of lambda. You have two eigenvalues which are real and negative. Number two, they are complex conjugates. So we plot again the imaginary of lambda and the real of lambda, and we have complex conjugate eigenvalues. To destabilize the fixed point, one or both of the eigenvalues need to cross into the right half plane as mu varies. With the saddle node, transcritical, and pitchfork bifurcations, we explored the cases in which a real eigenvalue passes through lambda is equal to 0. One now considers the other possible scenario in which two complex conjugate eigenvalues simultaneously cross the imaginary axis into the right half plane. The Hopf bifurcation comes in two flavors: a supercritical Hopf and a subcritical Hopf. We first discuss the supercritical Hopf bifurcation. Suppose that we have a physical system which has a control parameter mu, and for mu less than mu critical, for some critical value of mu, the system settles to some equilibrium through exponentially damped oscillations. So that's an example of damped oscillations when mu is less than mu critical. So if mu keeps increasing, at some stage the equilibrium state will actually lose stability. In many cases, the resulting motion is a small amplitude sinusoidal limit cycle oscillation about the original equilibrium state. So that's an example of a limit cycle where mu is greater than mu critical. In terms of the flow in phase space, a supercritical Hopf bifurcation occurs when a stable spiral changes into an unstable spiral which is surrounded by a small amplitude limit cycle. Hopf bifurcations can occur in phase spaces of any dimension n greater than or equal to 2. Now let's look at the example of a supercritical Hopf. So consider the system r dot is equal to mu r minus r cube and theta dot is equal to omega plus br square. In this particular system, we have three parameters. Mu controls the stability of the fixed point at the origin. Omega gives the frequency of the oscillations, and B determines the dependence of frequency on amplitude for larger amplitude oscillations. So consider mu less than 0. The origin r is equal to 0 is a stable spiral. For mu is equal to 0, the origin is still a stable spiral, though a very weak one. For mu greater than 0, there is an unstable spiral at the origin and a stable circular limit cycle at the square root of mu. Note that nearby trajectories get attracted to the limit cycle. To get a sense of how the eigenvalues behave during the bifurcation, we rewrite the system in Cartesian coordinates. So we write x is equal to r cos theta and y is equal to r sin theta. Then x dot is equal to r dot cos theta minus r theta dot sin theta, which is equal to mu r minus r cube times cos theta minus r times omega plus br square times sin theta, which is equal to mu minus x square plus y square and the whole term times x minus omega plus b times x square plus y square and the whole term times y, which is equal to mu x minus omega y plus cubic terms. And similarly, we get y dot is equal to omega x plus mu y plus cubic terms. So the Jacobian at the origin is A is equal to mu minus omega, omega mu, which has eigenvalues lambda is equal to mu plus minus I omega. So the eigenvalues actually cross the imaginary axis from left to right as mu increases from negative to positive values. We now outline two rules of thumb that hold generically for supercritical Hopf bifurcations. The first is that the size of the limit cycle grows continuously from 0 and increases proportional to mu minus mu critical square root for mu close to mu critical. The second is that the frequency of the limit cycle is given approximately by omega is equal to the imaginary of lambda evaluated at mu is equal to mu critical. This is exact at the birth of the limit cycle and correct within order mu minus mu critical for mu close to mu critical. The period is capital T is equal to 2 pi divided by the imaginary of lambda plus order mu minus mu critical terms. Now, like pitchfork bifurcations, Hopf bifurcations also have a supercritical and a subcritical variety. The subcritical case is much more dramatic and dangerous for engineering applications. We now consider a subcritical Hopf bifurcation. In this case, after the bifurcation, the trajectory must jump to a distant attractor, which may be a fixed point, another limit cycle, or off to infinity. So consider the following two-dimensional example. R dot is equal to mu r plus r cube minus r5 and theta dot is equal to omega plus br square. Note that the r cube term is destabilizing, i.e. it drives trajectories away from the origin. Now let's plot the phase portraits. With mu less than 0, we have a stable limit cycle and we have a unstable limit cycle. In this system, there are two attractors, a stable limit cycle and a stable fixed point. We also have an unstable limit cycle shown as a dashed curve. As mu increases, the unstable limit cycle starts to come closer and closer to the origin. A subcritical Hopf occurs at mu is equal to 0, where the unstable cycle shrinks to 0 amplitude and makes the origin unstable. Now we consider mu greater than 0. So we are left with a stable limit cycle. Now here are some notes. The large amplitude limit cycle is the only attractor in the system. The solutions that were close to the origin are now forced to grow into large amplitude oscillations. So let's look at an example. Consider the system x dot is equal to mu x minus y plus xy square, and y dot is equal to x plus mu y plus y cube. Show that a Hopf bifurcation occurs at the origin as mu varies. So let's look at the solution. The Jacobian at the origin is a is equal to mu minus 1, 1 mu, which has trace 2 mu and determinant mu square plus 1 is greater than 0, and lambda is equal to mu plus minus I. So as mu increases through 0, the origin changes from a stable spiral to an unstable spiral. Thus, a Hopf bifurcation takes place at mu is equal to 0, but the linearization actually does not tell us if the bifurcation is supercritical or subcritical. Now we note that analytical methods do exist that will help us to determine if the Hopf bifurcation is supercritical or subcritical. But the analytical methods can be quite difficult to use, and so one can first use computer simulations to develop insight into the type of the Hopf bifurcation. Now, the topic of discussion in this lecture was the Hopf bifurcation. The Hopf bifurcation is a very important one in both science and in engineering applications. Essentially, it's a bifurcation that leads to the birth of a limit cycle as a parameter in the system varies. It's worth mentioning that this bifurcation only occurs in dimensions 2 or higher, so it doesn't have a counterpart in one-dimensional flows. This bifurcation comes with two variants, a supercritical Hopf and a subcritical Hopf. In a supercritical Hopf, we get the birth of a small amplitude stable limit cycle as a parameter in the system varies. The subcritical Hopf is a more dramatic bifurcation where after the bifurcation the trajectory may actually go off to a completely different fixed point, may go off to a distant limit cycle, or may actually go off to infinity. So between these two variants, the subcritical Hopf is one that should be avoided, especially in engineering applications.